Hey everyone, welcome back to our Calculus 3 class notes here in section 15.8. And now we're on page 111 and we're talking about substitutions in triple integrals. So in other words, the stuff we just learned about making substitutions in double integrals, which remember substitutions in this case really means transforming the integral, really just extends kind of very straightforwardly into working with triple integrals. So that's kind of what I want you to understand. But what I want you to also remember is that the cylindrical and spherical coordinate system substitutions we did in section 15.7 are special cases of that substitution method, and I'm going to talk to you about that down in example 97 and show you how that works. Okay, so here's the theorem, the substitution theorem from triple integrals. So suppose I have a function of x, y, z and it's continuous over the region D. Let G be the preimage of D under the transformation x equals a function G, which has independent variables u, v, and w, y equals h of u, v, w, z equals k of u, v, and w. Assumed to be one-to-one on the interior of G. If the functions g, h, and k have continuous first partial derivatives with the interior of G, then this integral over the usual rectangular coordinate system x, y, and z can be transformed into the triple integral over G of f of, now x is g, h, and x is g, y is h, and z is k, but putting all the independent variables in terms of u, v, and w. Then I multiply that times the Jacobian of u, v, and w, the absolute value of the Jacobian of u, v, and w, times du, dv, dw. Where the Jacobian, again a straightforward extension, instead of a 2 by 2 determinant, it's a 3 by 3 determinant, which we have evaluated before when we did the cross product. So again, you take the first row, this partial vector with respect to u, then would be multiplied by the 2 by 2 determinant that is not directly under it. So it's like you take that partial derivative, get rid of that row, and then this column, and you're left with this 2 by 2. Then minus, we have to artificially insert a minus sign in here. In linear algebra, you learn about how that's cofactors, but for right now, just think about it as artificially inserting a minus sign here. Then the partial of x with respect to v times the 2 by 2, where I don't include that column or that row, so that's these guys, plus the partial of x with respect to w times the 2 by 2 that doesn't include the row or the column that guy's in. Okay, so we'll do that in example 97 with a couple examples.